Hello, my name is Cristian González Pérez, and I am going to talk to you about Formula 1 aerodynamics. First of all, I want to talk to you something. With your car, if you fail to take a turn, you know that the key is going slower. Well, in Formula 1, sometimes the key is going just a little faster. Let's take a look at the reason. Two main forces take their part in these cars. Drag, as you may know, opposes to the movement, like when you want to move a box over a carpet. And the downforce, that might sound new for you. Well, downforce is like lift in planes, but reverse. This force sucks the car to the ground because of the Bernoulli law that says that a longer distance to travel under the wing means a higher speed. And as the speed rises, the pressure decreases and the car is sucked down. That's good, but how can we calculate this? Let's move on to that. This formula let us calculate both the drag and the downforce. As you can see, it depends on the air density, the rho, that's like a P, the area, the surface area of the wing, a coefficient that depends on characteristics of the wing, the speed, and that stuff. And last but most important, the velocity up to the squared. That means that if the speed rises by a factor of 2, the force is multiplied by 4. As I said, this is the key in aerodynamics. And now, to finish my technical talk, not a TED talk, I need to present the Coanda effect. In a few words, it says that a fluid moving at a certain speed always tends to follow the shape of a solid. Well, I suppose that you haven't understood that, but let's take an example. Have you ever tried to transfer coffee from a cup to a glass? It always ends with coffee in the table. Well, the explanation is this effect. And now, after these technical explanations, let's move to the reality, starting with a little bit of history. The use of wings started with the Lotus 49 in 1967. The team mounted small wings in the front and the rear of the car that created downforce. Later, they changed the concept to high-mounted wings. That created a higher amount of downforce. Sadly, the concept was banned due to severe accidents and only small wings were allowed. The use of wings continued through the time until the present, but before, in 1978, the same team, Lotus, created the Lotus 79 that introduced the ground effect. The air was conducted under the car and accelerated, creating a huge amount of downforce. In the same year, the team Brabham went too far with this car that had a fan installed in the diffuser. In this way, the air could be accelerated at a higher speed, not depending on the speed the car was driving. After a little bit of history, let's move on to the present. As I said before, both the drag and the downforce depend on the same parameters and a unique coefficient. Here you have two totally different circuits, Monza and Hungaroring. Monza has long straights and just a few low-speed corners, whereas Hungaroring doesn't have long straights and have a huge amount of medium speed corners and low-speed ones. As you can imagine, these tracks have different requirements. For Monza, we need to minimize the drag that also comes with a reduction of the downforce, and for Hungaroring, we need the higher amount of downforce we can that also comes with a higher drag. Let's discover how can we change the car to adapt to these different tracks. Starting with the wings, you will take bigger ones for high downforce requirements and smaller ones for the opposite. At this point, you will vary the angle of attack to change the coefficient of the force. These elements generate both drag and downforce in a ratio of 2.5 in favor to downforce. However, new cars implemented the ground effect again, with safety improvements compared to the 70s. In this case, the drag generated is lower, and you can say, wow, we can achieve whatever downforce we want without any drawback. No, that's not the reality. Here we have a new phenomenon that's called porpoising. As the air is accelerated by the shapes underneath the car is sucked more and more and more, and at a certain point the car can touch the ground, collapsing and losing all the downforce, going up again and starting the cycle of bouncing. You can think, what's the solution? Well, the easiest one is raising the car, but this breaks the downforce. The exact solution is complex, and I'm not going to explain that because it's not the matter. Moving to another point, let's take a look at how the air is carried through the endplanes to reduce drag. As the air touches the sides of the car, it will follow the shapes until it reaches the diffuser or the rear wings, following the Coanda effect. To sum up, the aerodynamics are dominated by exact shapes and speed. We generate the drag that opposes to the movement and the downforce that sucks the car to the ground, resulting in the capability of taking the cars at a higher speed. Now I want you to dream about the future. What can we expect of the pinnacle of engineering and motorsport? To my mind, the future is in taking advantage of the active aerodynamics, having the exact grip, drag in the turns, the grip in the turns, and the lowest drag in straights. So that's all. If you have any question, any doubt, you can contact me via email. I hope you've enjoyed the presentation and that you have understood each point. Bye!